The universe around us seems to be made up of much more than what we can see. Indeed, the visible mass appears to be only a small fraction of the estimated total mass in the universe, and the observed motion of this visible mass suggests that it is mere flotsam on an invisible sea of unknown material. Galaxies are observed to rotate much faster than the visible matter in them requires them to. It would seem that invisible matter is stopping them flying apart. One explanation being postulated is that we are wrong to assume that gravity is unchanging and consistent over vast distances. Perhaps our current theory of gravity needs modifying. Another explanation could be that associated with each galaxy is an invisible halo of so-called dark matter, and it's this that's responsible for the galaxy's fast rotation. Looking for this dark matter will be CERN's Large Hadron Collider in Geneva, which will be on the hunt for an entirely new type of particle. It's long been known that particles such as electrons have a mirror twin with opposite charge. These inhabit the strange world of antimatter, loved of science fiction writers. In this case, the antimatter partner of an electron is a positron. In the presence of an electric field, they move in opposite directions. But CERN will be looking for an even stranger pairing. This is a photon. Like almost everything in the minute world of particle physics, it doesn't just sit there, it spins. The Large Hadron Collider will now be looking into the possibility that, say, this photon could have another type of invisible partner, this time not with opposite charge, but with different spin. The photino, as it's been dubbed, would spin at half the rate of the photon. This new family of sleeping partners have been christened supersymmetric particles, and may be waiting to be detected by the Large Hadron Collider. If the photino exists, it would have no charge, the same as the photon, but unlike the photon, it would have mass. But this would not form matter as we know it, because without charge, it would be incapable of forming the molecules that make up our familiar world. It could be that these supersymmetric particles will turn out to be the vast amounts of mysterious dark matter that shapes the universe around us. At the beginning of our universe, a minute blob of time and space, far smaller than an atom, began to expand as a way of dissipating its extreme energy. Such three-dimensional spatial expansion that happens everywhere and all around us is well represented by this two-dimensional surface of a balloon that is stretching as it's been blown up. The Big Bang into pre-existing space is now seen as the big stretch of space itself. After a moment of extraordinarily fast expansion, the blob seems to have contained a plasma of particles, including quarks and gluons. Then, as the energy density lowered, it seems that the Higgs field came into being, giving mass to the particles. On further stretching, the quarks and gluons condensed into protons and antiprotons, which almost annihilated each other. But not quite. The few protons left over formed the basis of the universe we now live in. 380,000 years after the beginning, energy was low enough to allow electrons to surround the protons and neutrons and form the first atoms. This neutral environment allowed photons to travel in straight lines. It was first light for the expanding universe. 200 million years from the beginning, gravity began grouping the first stars into galaxies. The clue to the concept of the big stretch came from the observation that when we from our galaxy look at a nearby galaxy, it only moves away slowly, whereas a distant galaxy rushes away at breakneck speed, as you would expect if they were on the surface of an expanding balloon. By colliding particles in CERN's Large Hadron Collider, it'll be possible to momentarily produce sufficiently high energy levels to mimic conditions that existed billions of years ago. Observing the results will enable scientists to glimpse interactions never before witnessed. By visiting earlier epochs, the Large Hadron Collider will be taking us on a journey back in time. Back to the very beginning. At last, mankind will be standing on the brink of the birth of our universe.